I will share my screen. Okay, can you see my screen? Can you hear my voice?
Yes, Doctor.
Okay, thank you for the response. So, if you see that my voice is echoed in the Google Meet, you should inform me as soon as possible. Maybe due to the technical problems. So, kalau suara saya ada gema sepanjang tempoh kelas ini, sila maklumkan. So, if there's any technical issues during this lecture session, please inform me as soon as possible. Okay. Okay, so last 2 weeks, okay, we have learned about this slide, which is about the which is about the FM and PM, okay, and we have stopped until this. I have explained about this. Maybe we should refresh again what we have learned so far, okay. So remember that okay, maybe we can start from the general equations for the angle modulation. So this is for both FM and PM. So the general equation is Vc sine 2 pi fct plus theta t. Okay, so I would suggest students to make a big bracket like this, so that you don't make the careless mistake. Okay, remember that all the parameters 2 pi fct and theta t belongs to the sine function. Okay, it belongs to the sine function. So theta t is a function of message signal VMT. Okay, and we have learned about theta t is the instantaneous phase deviation in radians, and then 2 pi fct plus theta t is what we call as the instantaneous phase, which is the exact phase of the carrier at the instant time, okay, at the specific time. So the unit is in terms of radians. And then we have another parameter what we call as the theta prime t. So theta prime t is the first deviation of theta t. Okay, so if you do the first deviation of theta t, d theta t over dt, so you will get this theta prime t. Okay, and again, if you want to find the theta t, so you need to do the integral of theta prime t. So integral of theta prime t dt. Okay, so this is the instantaneous frequency deviation, which is the frequency variations of the carrier in a given instant of time. And then we have another parameter what we call as instantaneous frequency, which is the first derivative of omega ct plus theta t. Okay, so we get omega c plus theta prime t. Okay, omega c is 2 pi f c. Okay, 2 pi f c. So we have seen that what is theta t, what is theta prime t. So theta t is kp vmt, theta prime t is kf vmt. So kp and kf is the phase and frequency deviation sensitivity parameter. Okay, so from these parameters we can define the, okay, so before that, so kp is phase deviation sensitivity parameter, kf is the frequency deviation sensitivity parameters. Okay, so the unit for kp is radian per volt, kf is radian per second per volt. So this is the unit. Okay, so from here we can define the complete equation for the phase modulation. Okay, so from the general equation Vc sine omega ct plus theta t. So we can rewrite the equation into Vc sine omega ct. So this is 2 pi f ct plus kp. So we replace theta t with kp vmt. So kp vm sine omega mt. So this is 2 pi fmt. Okay, so this is the equation for the phase modulation. Okay, so this is the general equation for phase modulation. Okay, vpmt. And we can also define the vfmt. Okay, so from the general equation Vc sine omega ct plus theta t, we can put inside the theta t equal to integral of theta prime t. Okay, so integral of theta prime t is integral of kf vmt. So we can put outside the constant parameters kf vm. Okay, vm is the peak amplitude of the message signal, and then we can do the integral of sine omega mt. Integral of sine, we can get negative cos. Okay, negative cos over omega m. Okay, so this is the general equation for vfmt. Okay, and remember to do the big bracket. Okay, so if you read from other literature books, okay, some of them use cosine function as the general equation. Okay, so no problem. So you can use a cosine function for the general equation, and you can also use the cosine function for the message signal. So normally we use sine and sine, or cos and cos. Okay, so we also have asked in the exam, we use a cos and also cos. Okay, cos for the general equations, and also cosine for the vmt equations. Okay, normally we choose like that. Either we give you sine and sine function, or cos and cos. So no problem, don't worry about that. Okay, we will give you the specific equations. So from there you need to do the calculation. Okay, so this is the this example asks you to derive the vpmt. So from the general equations, okay, Vc cos omega ct plus theta t. So we just need to replace theta t with kp vmt. So vmt is given in the question. So we can put kp vm cos omega mt. So therefore the equation become Vc cos omega ct plus kp vm cos omega mt. Remember, omega is equal to 2 pi f. Okay, this is 2 pi f m. Okay, and what about for the frequency modulation? vfmt, so vfmt is equal to, from the general equation, we need to replace theta t with integral of theta prime t. Okay, integral of theta prime t dt. Okay, so theta prime t is equal to kf vmt. Okay, so kf vmt is equal to kf vm cos omega mt. So we can put outside the constant parameters. Okay, and we do the integral of cosine. Integral of cosine would be positive sine. Okay, so positive sine over omega m. Okay, so therefore the final equation would be Vc cos omega ct plus kf vm over omega m sine omega mt. Remember to do the big bracket. This is very important. Okay, don't do careless mistake. Make sure you do the big bracket. Okay, because everything here belongs to the cos function. Okay, and we have seen from this graph previously that in the angle modulations, the frequency of the carrier change in accordance of the amplitude variation of the input message. Okay, so the amplitude variation of the input will change the frequency of the carrier. Okay, remember, in angle modulation, if the frequency of the carrier change, we are actually indirectly change the phase of the carrier as well. Okay, dalam angle modulation, both frequency and phase are related to each other. If we change the frequency of the carrier, we are also indirectly change the phase of the carrier as well. Okay, kalau kita tukar frekuensi, kalau carrier frekuensi berubah, maka secara tak langsung fasa carrier juga berubah. Okay, so both frequency and phase are related to each other. Okay, so in this slide, it wants to show you about the relationship of the carrier frequency in accordance with the amplitude variation of the input. Okay, so you see that here, this x-axis shows the range of carrier frequency. Okay, starting from the rest frequency Fc, okay, and then the minimum would be Fc minus delta F, and then the maximum of the carrier frequency is Fc plus delta F. And these frequencies of the carrier change in accordance with the amplitude variation of the VMT. Okay, so if you see from here, starting from the rest frequency Fc, the carrier frequency change to maximum frequency when the amplitude of the input message reach the peak amplitude. Okay, this is at Vm, and the carrier frequency becomes maximum Fc plus delta F. And when the amplitude of the input message change, okay, to the negative peak amplitude, negative Vm, what happened to the carrier frequency is that carrier frequency would be at minimum, which is Fc minus delta F. Okay, and so on. Okay, and when the amplitude is when the input amplitude is 0, so the carrier frequency would be at rest frequency, which is Fc. Okay, so these changes, delta F and delta F, okay, so the maximum changes would be 2 delta F. So 2 delta F is what we call as carrier swing. Okay, carrier swing. Okay, carrier swing is equal to 2 times delta F. Delta F is frequency deviation. Okay, delta F is frequency deviation. So carrier swing is 2 times the frequency deviation. Okay, and this picture, okay, so this picture I have explained previously, okay, in the class. So you see that you need to understand the concept of this waveform. So the first picture here is the carrier signal, which is VCT. Okay, and then the second picture here, the second graph here is a VMT. Okay, and then picture C here is VFMT, and then graph D here is a VPMT. Okay, and how to understand the waveform? Okay, how to understand the waveform? So let's look for the frequency modulation wave. Okay, so if you want so if you see from picture C and D, we cannot differentiate whether this is FM or PM, because both waves look similar. Okay, we cannot, if I just give you wave C and D, you cannot differentiate whether this is FM or PM. Okay, so in order to differentiate both of the waves, you need additional information about the carrier and also about the modulating signal or message signal. Okay, if you have two of these waves, then we can differentiate whether this is FM or PM. Okay, so memang tak dapat nak bezakan kalau tidak ada rujukan VFMT dan juga rujukan VMT dan juga VCT. Okay, so if you see from picture C, graph C, okay, so starting here, the carrier frequency would be at rest frequency. So rest frequency is equal to FC. Okay, rest. Okay, initial state. Okay, and then what? Then the modulating signal moves from 0 until peak amplitude. Okay, so what happened is that this is a peak positive amplitude. What happened is that the carrier frequency would be at minimum, which is FC minus delta F. Okay, so that's why at this point carrier frequency would be at minimum, which is FC minus delta F. So that's why you see the ripple is further away from each other. The ripple is not close. It's not close one another. It's further away from one another. Okay, and then what? Then the VMT moved from positive peak, and then it reached the x-axis, or what we call as the zero crossing. Zero crossing is the x-axis. Okay, when the wave want to change the polarity from positive to negative or negative to positive. So this is the point where we call it as zero crossing. So at zero crossing, okay, carrier frequency would be at rest frequency. What is rest? Rest is at FC. Okay, and then the VMT moves towards negative peak amplitude. What happened? So what happened to the carrier? It will have the maximum positive deviation. Okay, and you see that the ripples is very close to one another. This is what we call as the maximum positive deviation, and the carrier frequency would be at maximum, which is FC plus delta F. Okay, and then what? Then the VMT moves towards zero crossing, so the carrier frequency would be at rest, okay, which is FC, and so on. Okay, dan seterusnya lah. Okay, so you see that for frequency modulation for VFMT, the critical changes happens when the modulating signal achieve the maximum peak amplitude positive or maximum negative peak amplitude. So the critical changes during the peak amplitude of the input message. Okay, whereas for the PM, okay, phase modulation, if you see graph D, okay, you will see later that the critical changes happens during the zero crossing. Okay, so I will erase this one. I will erase. Okay, so initially the carrier frequency at rest frequency, which is FC, and remember for the PM, for the phase modulation, critical change happens during zero crossing. So this is, you see that starting from 0, it moves towards positive. Okay, and you see from here, at this point, the frequency of the carrier is at peak amplitude. Okay, which is, sorry, the frequency of the carrier is at the highest frequency. Sorry. which is Fc plus delta F. Okay, maximum. And then VMT achieve peak amplitude, peak positive amplitude. What happened? What happened is that the carrier frequency would be at rest, which is Fc, rest frequency. Then the modulating signal move towards zero crossing, towards negative side, towards negative polarity. What happened? Okay, what happened is that critical change happens. The frequency of the carrier becomes minimum. Okay, so the carrier will achieve the maximum negative deviation, which is Fc minus delta F, minimum frequency carrier. Okay, and then what? The modulating signal achieve the peak negative amplitude. What happened to the carrier? The carrier would be at rest frequency. Okay, at rest frequency means that at Fc. Okay, and then what? The message signal moves from negative peak towards zero crossing. It wants to move towards positive. Okay, what happened? It will be critical change to the carrier. Okay, so the carrier will be at maximum positive deviation, means that the carrier frequency would be at maximum, which is Fc plus delta F. Okay, and so on, dan seterusnya. Okay, so you see that for phase modulation, critical change happens during zero crossing. Okay, critical change for the carrier happens during the zero crossing, while for the frequency modulation VFMT, critical change happens during the peak amplitude of the input message. Okay, so you need to understand where does the critical change happens. Di manakah berlakunya perubahan yang kritikal? Okay, so for FM, critical change happens during the peak amplitude of the input message. For phase modulation, critical change happens during the zero crossing of the input message. Okay. So previously we have asked this kind of question where the student needs to understand about the critical changes. Okay. So you need to understand what happens during the critical changes, especially for the carrier frequency. Okay. So phase deviation. Okay, phase deviation. Phase deviation and modulation index. Okay. So based on the PM equation, which is Vc sine in bracket omega Ct plus this is actually KPVM. So remember that equation 3.2. If you see equation 3.2 from these equations, we can actually replace KPVM with modulation index parameter, which is beta P. Okay, so if you go this slide, okay, so this is actually Vc sine in bracket in bracket 2 pi fct plus kp Vm sine 2 pi fmt. Okay, so we can replace kpvm with beta p. Okay, so beta p is a modulation index for phase modulation equation. Okay, beta p is a modulation index for PM, phase modulation. Okay. So one of the primary difference between PM and FM is how the beta P is defined. Remember, for this beta P, it has the unit which is in radians. So beta P is in radians, and it is sorry, this is supposed to be capital VM, and this is the peak amplitude of the input message. Okay, KP times VM, peak amplitude. Okay, so what's the difference? Okay, we're gonna see later about beta F for the FM. Okay, so for PM, modulation index is proportional to the amplitude of the modulating signal independent of its frequency. So you see that beta P, okay, beta P is proportional to the peak amplitude of VM. So the higher the value of VM, the higher would be the modulation index for PM. Okay, and it is not depending on the frequency of the input message. So regardless of the input message frequency, the beta P is not changed. It does not depending on the frequency of the input message. Beta P only depends on the peak amplitude of the input message. Okay, and you're gonna see later what happened to the beta F for the FM. Okay, so before we see about for FM, we're gonna see later about for FM we call it as beta F. Okay, for PM we call it as beta P. Okay, beta P. So beta P is equal to Kp multiplied with Vm. Remember, for Kp is the phase deviation sensitivity parameter. The unit is radians per volt multiplied with Vm. So Vm is in terms of volt. So radian per volt multiplied with volt, you're gonna get radians. So that's why beta P in radians. Okay. What about beta F, which is the modulation index for the frequency modulation? Okay. So based on the FM equation, which is this one, if you remember, if FM equation is Vc sine in bracket 2 pi fct minus kf Vm over 2 pi fm cos 2 pi fmt, close big bracket. Okay, so we have seen this equation previously for Fm, and the whole thing in front of the cosine function is what we call as the modulation index beta F. Okay, so beta F is equal to Kf Vm over omega m, or over 2 pi fm. Okay, and there's no unit for the beta F. So beta F is unitless. Okay, it's a unitless parameter. Beta P has a unit radians. Okay, previously beta P is in terms of radians, while beta F is a unitless parameter. Okay, why is a unitless parameter? If you see from here, Kf parameter is equal to the unit for Kf is radian per second per volt, and then you multiply with Vm in terms of volt, and then you divide with radian per second. Okay, so this one, volt and volt, you can cancel out, and then radian per second divide with radian per second, so it's gonna be a unitless parameter. Okay, so beta F you can write like this. So beta F is equal to kf Vm over 2 pi m. Okay, so we can also write, so this is the unit is radian per second per volt. We can also write beta f like this in term of kf Vm over Fm. Okay, so we can write also beta f like this, kf Vm over Fm. Okay, so that means this kf has a different unit, which is in term of hertz per volt. Okay, hertz per volt. So if this kf is in term of hertz per volt, you multiply it with volt, you divide with hertz, so it is a unitless parameter. Okay, so for this equation, it's actually you divide the above and below with 2 pi. Okay, so that's why you get a kf in term of hertz per volt. Okay, so normally most of the time in the exam we use beta f as this one, hertz per volt. Okay, we use this parameter to calculate the beta f normally in the exam. Okay, so we give you the value of kf, and then you need to find the beta f. Okay, so if the kf is in term of hertz per volt, so you need to use these equations to find the beta f. Okay, so this is actually similar with this one actually, but for this one we divide the denominator and the above one with 2 pi. So that's why this one and this one is actually similar, but for this beta f equations we divide both above and below, I forgot, denominator and numerator if I'm not mistaken, with 2 pi. Okay, so that's why it becomes hertz per volt multiplied with volt divided with hertz. Okay, frequency deviation delta f and also phase deviation delta theta. Okay, so delta f is equal to kf Vm, while delta theta is equal to kp Vm. Okay, so this is define the change of the carrier parameters either in term of frequency, which is delta fc, or in term of phase, which is delta theta. Okay, so this delta is the changes, the variation. Okay, the changes happens in the carrier parameters. Okay, delta perubahan, the changes. Okay, so for example, a sample transmitter with assigned rest frequency of 100 megahertz. Rest frequency means that fc. Okay, rest frequency deviated by a plus minus 25. The carrier change frequency with modulation between limits of 99.975 and 100.025 megahertz. So you see that if we draw the frequency spectrum, okay, so this is 100. Okay, this is in term of megahertz. Okay, and the changes happens for about plus minus 25. So this is 100.025. Okay, because this is just 25k. This is in term of mega. So this is see that here is, so the carrier change 100 mega minus 25k, so 99.975 megahertz. Okay, so this is delta f, this is also delta f. Okay, delta f or delta fc. Okay, so you can write either delta F or you can write delta FC, so no problem. Okay, both are the same. Okay, and both of these delta F and delta F is what we call as the carrier swing. Okay, so this is 25k, another 25 kilohertz. So that means the carrier swing is equal to, okay, carrier swing is equal to 2 times delta F, which is equal to 50 kilohertz of carrier swing. Okay, so table 1 display the transmission band used for FM and the legal frequency deviation limit for each category. So we're going to see later about table 1. Okay, so deviation limits are based on the quality of the intended transmission. Wider deviation results in high fidelity. So the frequency deviation is useful parameter for determining the bandwidth of the FM signal. Okay, so the larger the value of delta F, the wider would be the bandwidth of the signal. Okay, lagi besar nilai delta F, lagi besar dia punya bandwidth. Okay, and then what? So since beta F is equal to kf Vm over 2 pi Fm, so we can replace kf Vm with delta F. Okay, remember kf Vm is delta F. Okay, so delta F divide with Fm. Okay, so remember this is kf Vm over Fm. So this kf Vm we can replace with delta F. Okay, so if you put in the equation, okay, if you put in the equation, this is we can replace kf Vm with delta F. So this is Fm equation. Okay, Fm equation. So Vc sine 2 pi Fct plus minus, this is actually beta F. Okay, so beta F becomes delta F C over Fm. So this becomes delta F. Okay, what is delta F? Delta F is kf Vm. Okay, so delta F is equal to kf Vm. Okay, we just replace it. Okay, we just replace it, so don't confuse. Okay, kita cuma gantikan sahaja. Okay, so delta F over Fm is what we call as the beta F modulation index. Okay, delta F is the frequency deviation. Okay, so depending on the value of the modulation index beta F, we may distinguish two cases of frequency modulation: narrowband FM and wideband FM. Okay, so narrowband and wideband is depending on the value of beta F. Okay, so the higher the value of beta F, it's gonna cause a wideband FM. Okay, wideband means a high bandwidth of FM. If the value of beta F is small, we call it as narrowband. Narrowband means the bandwidth is small. Okay, so the bandwidth of the FM is depending on the value of beta F. The higher the beta F, the higher would be the bandwidth. Okay, so lagi besar nilai beta F, lagi besar bandwidth untuk FM signal ini. Okay, so we're gonna see these two types of FM, narrowband and wideband FM later. Okay, kita akan lihat nanti. And this is table 1. Okay, the table 1. So table 1, what is important is for the first row only. Okay, the first row here. Okay, the first row about the commercial FM radio broadcast. So frequency assignment for the FM, okay, FM frequency band is between 88 until 108 megahertz. So if you tune in your radio, you're gonna get from 88 until 108. Okay, so there's gonna be around 100 stations in the within the specific band. So within that specific band, 88 until 88 until 108. So this is around 20 megahertz of bandwidth. Okay, 20 megahertz of total bandwidth, which can accommodate many radio stations at a given specific area. Okay, so each radio station or each channel has the bandwidth of maximum 200 kilohertz maximum. Okay, and then maximum deviation, this is maximum delta F. Delta F maximum is equal to plus minus 75 kilohertz. Okay, plus minus above and below of the frequency limit. Okay, and the highest audio means highest FM max is 15 kilohertz. Okay, and the other rows is about televisions, sound. This is for public safety applications, amateur radio, wireless mics, videotape, satellite applications, and so on. Okay, so we're gonna see later. We're gonna see about the first row here for the commercial FM. Okay, so percent modulation. Okay, before that, so you see, so you see that from 88 until 108 megahertz. This is the standard FM frequency band. So this is actually referring to the carrier. Okay, the carrier frequency can be any frequency between 88 until 108 megahertz for the FM broadcasting. Okay, untuk FM broadcasting, carrier frequency can be any frequency between 88 until 108, which is the broadcast frequency. The broadcast frequency is the carrier frequency. Okay, and another parameter is what we call as the percent modulation. Okay, percent modulation. So simply the radio frequency deviation actually produce the maximum frequency deviation allowed by the law stated in percent form. So we compare the delta F actual with the maximum delta F, which is defined by the standard or by the law stated by the government. Okay, for example, we already known about delta F max from table 1. So delta F max is 75 kilohertz. This is the maximum allowed by the standard. Okay, and we compare this with the delta F actual. Okay, so for example, if a given modulating signal produce plus minus 50 kilohertz, so this is delta F frequency deviation, and the law stated that the maximum frequency deviation allowed is plus minus 75 kilohertz. So this is the maximum. Then find the percent modulation. So percent modulation is equal to delta F actual divide with delta F max. Okay, multiplied with 100%, so we get 67%. Okay, 67%. Okay, so if you have question about this, you can ask. Otherwise, we will move to the next example. Okay. Okay, so starting from here, we're gonna have many calculation examples. Okay, we have many calculation example, so let's try to do it. Okay, let's try to do it. So please open your calculator, switch on your calculator. Okay, so a 1 megahertz carrier frequency with a measured sensitivity of 3 kilohertz per volt is modulated with a 2 volt 4 kilohertz of sinusoid. What is this actually? So the question said that 1 megahertz of carrier, so that means this is FC. Okay, and then with the measured sensitivity parameter of 3 kilohertz per volt. What is this? This is actually referring to the KF. Okay, the sensitivity parameter, frequency deviation sensitivity parameter. Okay, so this carrier is modulated with another signal which has the peak amplitude of 2 volt and frequency of 4 kilohertz. So what is this? This is actually referring to the VM, peak amplitude, and also FM. Okay, the modulating signal frequency or the message signal frequency. Okay, and then what? Determine the first question, the maximum frequency deviation of the carrier. So the first question asks about delta F, frequency deviation. Okay, frequency deviation is equal to KF VM. Okay, so this is equal to so you can put inside here is 3 kilohertz per volt multiplied with VM. VM here is 2 volt, so you're gonna get 6 kilohertz. Okay, 6 kilohertz. And then what? Determine the modulation index, beta F. Why beta F? Because this is about frequency modulation. Okay, this is about frequency modulation. So beta F is equal to KF VM over FM, or this is equal to delta F over FM. Okay, so this is equal to delta F over FM, which is 6 kilohertz. So 6 kilohertz divide with 4 kilohertz. Okay, so you get 1.2 on 1.5, 1.5. Okay, so delta F over FM, or KFBM over FM. Okay, we get 1.5. And then what? Number 3, find the modulation index, beta F, if the modulation voltage is double. So that means the modulation voltage from 2 volt becomes 4 volt. Okay, so VM is equal to 2 times 2 volt, so it becomes 4 volt. Okay, so now the modulation index is equal to beta F is equal to KF VM over FM. So this is equal to 3 kilohertz per volt multiplied with 4 volt divide with so the FM, the message frequency is still the same, which is 4 kilohertz. Okay, so this becomes, so 12 divide with 4, you're gonna get 3. Okay, so you see that if you double the modulation voltage Vm, you will also double the modulation index. Okay, so from 1.5 becomes 3, so double. Okay, and then what? Determine the modulation index beta f if you are given VMT is equal to new one. Okay, so 2 cos 2 pi 8 kilohertz. Okay, so you see that this is Vm 2 volt, and you are given new FM frequency, which is 8 kilohertz. So previously is 4 kilohertz, now you are given the FM frequency is 8 kilohertz. Okay, so the message frequency becomes double in this number 4. Okay, so what happened is that we will find the beta f. So beta f is equal to kf Vm over Fm. So this is equal to, kf is 3 kilohertz, so 3 kilohertz per volt multiplied with Vm is 2 volt. Okay, divide with 8 kilohertz. Okay, so you will get this equal to how much? So this will become 0.75. Okay, 0.75. Okay, you can use your calculator. So this 6 divided with 8, so you get 0.75. Okay, so the next question, express the FM signal mathematically for a cosine carrier and cosine modulating signal of part 4, which is this one. Okay, carrier amplitude is 10 volt. So for this number 5, you need to understand about the FM equation, FM general equation. Okay, remember VFMT is equal to VC sine something, but remember the question said that you are given in term of cosine. Okay, so that means you just need to change from sine to cos. So that means cos, okay, big bracket, remember this is 2 pi fct, okay, plus this is beta f cos, it becomes cosine modulating signal, it becomes a sine. Okay, so if you have cos, it will become sine. Okay, it become sine. Sine, this is maybe I will do like this. Kf Vm integral of cos dt, cos cos 2 pi fm t dt. Okay, like this. Okay, so you will get this like this. So you will get this Vc cos 2 pi fct plus kpvm over 2 pi fm 2 pi fm sine 2 pi fm t. Okay, integral, of course you're gonna get positive sign. So kp vm over 2 pi fm, so this is actually referring to beta f. Okay, beta f. Beta f of what? Beta f from part 4. Okay, because we already calculate the beta f from part 4. Okay, so this is actually equal to, sorry, this is kf, not kp, sorry, kf vm over 2 pi fm. Okay, so this is actually equal to kf vm over fm. If we make the kf as hertz per volt, okay, if we divide above and below of the ratios, we're gonna get kf vm over fm. Okay, which we already calculate in question number 4. Okay, we already calculate from equation number 4. So therefore vfmt is equal to, so we can put inside the equation, we can put inside the parameters, the given parameters. So vc, carrier amplitude, is given as 10. So that means 10 cos, okay, in bracket 2 pi fct, 2 pi in bracket 1 times 10 power of 6. So this is 1 mega, okay, plus 0.25, okay, which is beta f. So this is 0.25, sorry, 0.75, 0.75 sine 2 pi in bracket. So now the frequency of fm is 8 kilohertz from part 4, okay, which is 8 kilo. Okay, and remember to close the big bracket. Okay, so this is the answer. Do you have question about this? You can ask. Okay, so the 0.75 is actually kf vm that we have calculated from part 4. Okay, question number 4, which is 3 kilohertz multiplied with 2 volt divided with modulating signal frequency 8 kilohertz. So we get 0.75. Okay, which is this one. Okay, so if you have question, you can ask. Otherwise I will move to the next example. Okay, otherwise I will move to the next example. Okay, so no question. So let's look from another example. Okay, so this is the summary of the equations. So you don't need to memorize all of this. Okay, you don't need to memorize all of this. Okay, because this is you will see you already seen these equations. You already seen these equations. These equations also you have learned. Delta F also you have learned. Also you have learned this one. So you have seen all of this. Okay, you have seen all of this actually. Okay, so no need to memorize all of this. Okay, so you need to understand it so that you can use it when the time needs. Okay, so the final exam now is open book, so you can refer these notes later. So you don't need to memorize everything. Okay. Okay, so let's let's move to this part. Okay, so I think is it okay. FM radio frequency. So this is also one of the favorite question in the final exam. Okay, so we have asked this example many times in the final exam. Okay, kita pernah tanya soalan ini banyak kali dalam final exam. This is a very simple question. Okay, so you see that you are given that the FM frequency band is between 88 megahertz until 108 megahertz. Okay, so each station or each channel allotted to a frequency deviation of 75 kilohertz of this is a delta F. This is delta F. So that means each channel or each radio station has the frequency deviation of plus minus 75k. Okay, so if you plus minus above 75, below 75, so total gonna be 150 kilohertz. Okay, so before that maybe we can draw so that you can have a better understanding. Okay, so let's say that this is F. So 88 is somewhere here until 108. Okay, so within this frequency band, there are many radio stations. So now the issue is how many radio stations that we can allocate in this frequency band. Okay, so it is said that for each channel or each radio station, okay, so for example here we find the radio station, for example here, radio station. So this radio station, for example, we're gonna give a FC at a certain frequency, and it is said that the frequency deviation given is here is 75k, okay, and also 75k. Okay, so maybe I change the color. Okay, so 75k until here, 75k until here. Okay, so total in this one, if you see from here, this one the range is 150. Okay, 75 and 75, so 150 kilo. Okay, and it said that it give another 25k for the guard band. So the guard band is actually to guard the channel from adjacent interference. Okay, so actually we have another 25k over here, and also another 25k over here. Okay, 25k, 25k. Okay, so that's why here the total becomes 200 kilohertz for each radio station. So each radio station, the bandwidth is 200k. So now the question is, how many radio stations we can allocate inside the FM band? Okay, so you see that the total bandwidth of the bandwidth, okay, the total band for the FM is 108. So you see that okay, so the number of station. So the number of station is equal to so we need to divide. So 108 mega minus 88 megahertz. So this is the total, okay, the total band for the FM, and we divide the total band with the channel bandwidth. Each channel has a 200 kilohertz of bandwidth. Okay, satu channel 200. Okay, one channel 200K. So now the issue is how many radio station we can allocate. Okay, so therefore we get this 100 station. Okay, so 108 minus 88 mega, which is 20 mega. 20 mega divided with 200K, so we get 100 station. Okay, so we have asked this question many times in the exam, so this is like a bonus question. Okay, if you have question you can ask, otherwise I will move to the next example. Okay, narrowband frequency modulation. Okay, so remember previously we have seen that FM has two categories, which is narrowband FM and also wideband FM. Okay, so for narrowband FM, the bandwidth range from 10 to 30 kilohertz, small bandwidth. Okay, so modulation indices are generally kept near unity so that the FM bandwidth can be determined in a similar manner as the AM system. Okay, so beta F is small. Okay, beta F is small, and therefore we can determine the bandwidth, which is approximately equal to the double sideband full carrier, which is 2 times FM. Okay, so how comes it become like this? Okay, how come the bandwidth is approximately equal to 2 times FM? So we're gonna see later about this. We're gonna see later why the bandwidth is calculated like this. Okay, so the beta F is small, okay, which result in bandwidth equal to 2 FM. Okay, this beta F must be small enough so that the bandwidth can be calculated as 2 times the modulating signal frequency. Okay, so if you see from here, this system for narrowband is widely used for the mobile radio systems for the police, fire and taxi services. Okay, and also for the amateur radio. Okay, so now we're gonna see what is the equation for the narrowband. Okay, so assume that the carrier signal frequency, carrier signal equation is Vc cos omega Ct, and this carrier is modulated with modulating signal, which is Vm cos omega Mt. Okay, and this resulting in the FM equation. Okay, we have seen this general equation before, which is equal to Vc cos omega Ct plus beta F sin omega Mt. Okay, so this is the FM general equation. Okay, we have seen before, kita telah melihat equation ini previously. We have seen this equation previously. So this beta F is actually Kf Vm over Fm, or Kf Vm over 2 pi Fm, depending on the unit of Kf. Okay, so normally we use Kf Vm over Fm for the beta F. Okay, so sin omega Mt. Okay, so you see that this is positive because we use both cos and cos. Okay, so now we want to look inside the equation. If we rearrange, if we rewrite the equation, what happened actually? Okay, so since this is narrowband FM, so beta is small. Okay, normally less than 0.25 normally. Okay, so if beta is small, we can approximate a few parameters. Okay, we can do approximation of a few parameters. Okay, if beta is small, we can make approximation for some parameters. Okay, for example of this, we're gonna see about this later, both of these. So this is based on the trigonometry functions, that we can get this one approximately equal to 1, and this one is approximately equal to beta F omega or Mt. So what is this actually? What is this? Okay, So we want to rewrite the equations. So that means you see that here is VC cos A plus B. So within the cosine function, there are two parts, A and B. Okay, so cos A plus B. Okay, so this is actually like the VC cos A plus B. Okay, where A is the omega CT, B is the beta F sine omega MT. And according to trigonometry identity, we can rearrange these equations, okay, to become like this. Okay, according to trigonometry identity, cos A plus B is actually equal to cos A cos B minus sine A sine B. Okay, so this is based on the trigonometry identity. Okay, therefore we can put inside the equations, okay, cos A is cos omega CT. What is cos B? Cos B is equal to this one, cos of B. Okay, cos of beta sine omega MT is approximately equal to 1. Okay, so this has been approximated. Okay, approximately equal to 1. So we multiplied with 1 actually over here. Okay, with 1 minus sine A sine B. Sine A is VC sine omega CT. Sine B, what is sine B? So sine B is equal to sine of B. That means sine of beta F sine omega MT approximately equal to beta F sine omega MT. Okay, so we put inside the equation. So this is sine B, beta F sine omega MT. Then what? So you see that this this part is sine and sine. So we can further elaborate the equation. Okay, sine and sine, according to trigonometry identity, it becomes half of cos A minus B minus cos A plus B. So we have seen this equation in the amplitude modulation previously. Okay, so now we want to rewrite the equation. Okay, so therefore we can put VFMT equal to VC cos omega CT from this part, okay, and sine become cos minus cos. Okay, so 1 over 2 beta F VC, okay, beta F VC, so this is beta F VC cos 2 pi, this is FC plus FC minus FM. Oh, so in here, this is supposed to be lowest sideband. Okay, sorry. So this is, since this is plus, so we just rearrange the equation. And so you see that this is supposed to be initially is minus, initially is minus. So now it is supposed to be, if you want to make it minus, so this is lower sideband and upper sideband. But now from here it put plus over here, so plus means that we start with so this upper sideband becomes positive, because we multiplied with minus. So 1 over 2 beta F VC cos upper sideband minus cos of lower sideband. Okay, so remember this is big bracket over here. Okay, so we have 3 components now. Okay, so if you want to rewrite the equation, it becomes like this. So Vc cos 2 pi fct plus beta f Vc over 2 cos 2 pi fc plus fm, the upper sideband, so this is okay, minus the lower sideband, which is beta f Vc over 2 cos 2 pi fc minus fm. Okay, so you see that we have three components now. We have the carrier, we have the upper sideband, and we have the lower sideband. And if we want to draw the spectrum, so now we can draw the spectrum because we already have the complete equation. Okay, so if you draw the frequency spectrum, it's gonna be like this. Okay, so the carrier component, which has the amplitude of Vc, this one, Vc, and the sideband has the amplitude of beta f Vc over 2. Okay, for the upper and lower sideband. Okay, and you see from here the bandwidth is how much is the bandwidth? So this is the distance. You see the fm and fm, so the bandwidth is equal to 2 times fm. Okay, 2 times the modulating signal frequency, so which is similar with AM double sideband full carrier. Okay, so even for FM, this is for frequency modulation. Okay, for frequency modulation, bandwidth of 2 FM is considered as small bandwidth, whereas for the AM, remember when we learn AM double sideband full carrier, it is considered as big bandwidth. Okay, but that one is for AM. For FM, for frequency modulation, bandwidth of 2 FM is considered as small. So that's why the term is used as narrowband. Okay, so narrowband FM is similar with AM double sideband full carrier. Okay, untuk narrowband FM dia adalah mirip kepada double sideband full carrier. Okay, so what about the wideband FM? Wideband FM. So wideband FM, if you see from here, we can derive the equations. So wideband FM. So the word wideband means that big bandwidth. Okay, perkataan wideband ini merujuk kepada bandwidth yang besar. Okay, so how to determine the bandwidth? Okay, so the bandwidth is actually depending on the value of beta modulation index. Remember previously I said that the higher the modulation index, the higher would be the bandwidth. Okay, so that means, okay, so first we need to understand the general equation for frequency modulation, which is Vc cos 2 pi fct plus beta sine 2 pi fmt. Now the issue is, how big is the bandwidth? It is depending on the value of beta. Okay, so it does not have a specific bandwidth, and we need to determine the bandwidth based on the given beta. If we know the beta, then we can calculate the bandwidth. Okay, so how to do that? We can use the Bessel function to determine the bandwidth. Okay, so this is the Bessel table. Okay, this is the Bessel table. Normally in the final exam we will give you this table. Okay, normally in the final exam we give this table. So you need to understand what is this actually. Okay, so when I want to explain about this, so if you see from this table, so perhatikan class, so listen carefully. So see that the first column is what we call as the modulation index, beta f parameter, and beta f parameter starting from 0 until 8. So that means from lower to higher values. Okay, and then what we have, the carrier component. The second column is carrier component, okay, which is J0. Okay, and the rest of the column is the sidebands components, okay, from J1 until J10. What is this actually? So when you draw the spectrum, okay, when you draw the spectrum, so the carrier, okay, at frequency Fc, okay, so this is J0, okay, and then the sideband, okay, the first sideband is J1, and then J2, and so on. So J0 until J10 is what we call as the relative amplitude. Okay, so J is a unitless parameter. Okay, so Jn, so the general equation is Jn is equal to Vn over Vc. Vn is the real amplitude. Okay, Vn is the actual amplitude divide with Vc. So you get a relative amplitude. Relative amplitudes here means relative to the carrier amplitude. Okay, so J has no unit. Okay, and if you see from here in this table, negative polarity, for example like this one, this is referring to the phase shift. Okay, so if phase shift happens, the polarity will change to negative. Okay, and it's already stated here that the negative sign means that it is 180-degree phase inversion. Okay, 180-degree phase shifts happen at that time, so that's why the polarity changed to negative. Okay, so if you see from this table, okay, you see that from this table, for example, this one, beta equal to 1.0. Okay, so we have up to J3. We have the carrier component and we have up to 3 pairs of sideband. Okay, so this J is actually pairs of sideband, pasangan sideband. Okay, so that means if the beta is equal to 1, we're gonna have carrier component, upper sideband, we have 3 upper sideband and 3 lower sidebands. Okay, I repeat again, if beta equal to 1, we're gonna have carrier component and 3 pairs of sidebands. That means 3 upper sideband and 3 lower sideband. Ada 3 pasang. Okay, and here dash means that we don't have any other sidebands. Okay, and remember for this table, it has neglect the value less than 0.01. Okay, this table has neglect the value less than 0.01. So if the sideband has the value 0.0001, it has been neglected from the table. Okay, so we're gonna use this table in the exam, okay, to calculate the given questions. Okay, so for example, if we go to higher number of beta, for example beta equal to 8, okay, beta equal to 8, so we have carrier component and also 10 pairs of sideband. 10 pasang sideband. Upper sideband and lower sideband. We have 10 upper sideband and 10 lower sideband, which is very big. So, the higher the value of beta, the wider would be the bandwidth. Okay? So, lagi besar nilai beta, lagi besar nilai bandwidth. Okay? So, this is how you need to understand the table. Okay, because you're going to use this table to do the calculation. Okay, and this is example. For example, this is up to 6 FM. Okay, so wait. This is so you see that for if the value of beta is 1. Okay, if the value of beta is 1, that means I'm gonna have up to 3 pairs of sideband. This is just example. I just want to show example. So we have up to J3. Okay, and what about the frequency? So FC, so this is FM, this is 2 FM, this is 3 FM. Okay, this is sorry. Yeah. So this is FC plus FM. This is FC plus 2 FM. Another one here is FC plus 3 FM. And over here is FC minus FM, FC minus 2 FM, FC minus 3 FM. Okay. So if you have beta equal to 8, that means we're gonna have up to J10. Okay, up to J10, and up to here is J10 means that here frequency is FC plus 10 FM. Here is FC minus 10 FM. So very big bandwidth. Okay, the larger the bandwidth becomes bigger. Okay, so for example, like this is up to 6. If you see up to 6, which one is up to 6? For example, like this one, up to 6 pairs of sideband. That means the beta in that example is 3. Okay, if beta is 3, we're gonna have up to 6 pairs of sideband, which is like this. Okay, beta equal to 3. Okay, up to 6 pairs of sideband. Okay, so that table is actually derived from this Bessel function graph. Okay, the value in the table is actually defined from this graph actually. Okay, so this is a Bessel function. This is the Bessel function figures. So from here you see that this is J versus modulation index. So if you have a ruler, okay, if you have a ruler, you can cross the line using your ruler. For example, beta equal to 1. So beta equal to 1 will cross at J3, it will cross at J2, and then cross at J1, and then cross at J0. Okay, so the value of crossing, okay, the crossing value is defined in the table. Okay, nilai-nilai crossing ini adalah nilai dalam table. Okay, the value of the cross here is given in the table. Okay, so that's why we have the value J0, J1, J2 and J3 for beta f equal to 1. Okay, for example like this one. Okay, beta f equal to 1, we have these three values, 0.77, 4411 and 0.02. Okay, So for the other beta values, you can use your ruler, and you can find the value. Okay, and now since we are in the internet era, so we can actually search from the Google about Bessel function. So if you search in the Google, you're gonna get a complete list of table for the Bessel function. Okay, and so on. So all right, so what's next? Okay, transmission bandwidth. So now the issue is, how can we calculate the bandwidth? Okay, how can we calculate the bandwidth for the wideband FM? Macam mana nak kira? Okay, so there are two ways to calculate the bandwidth of the wideband FM. The first one is to use the Bessel function. Okay, bandwidth by Bessel. Okay, bandwidth by Bessel is equal to 2 times n times FM hertz, where n is the number of significant sideband. Okay, so n is referring to the number of pairs of sideband. How many pairs of sideband? For example, in the previous table, beta f equal to 1, for example, we have up to 3 pairs of sideband. So this is actually referring to the n. Okay, if we look in the table, okay, beta f equal to 1, we have up to 3 pairs of sideband. Okay, up to 3 pairs of sideband. That means n equal to 3. Okay, 3 significant sideband. Significant sideband means how many pairs of sideband. Okay, so here 2 times 3 times FM, the value of modulating signal frequency. So this is if beta equal to 1. Okay, so we're gonna see example, this one, example. So calculate the bandwidth occupied by FM signal with a modulation index of 2. So beta f is equal to 2. Okay, beta f is equal to 2, and the highest modulating signal frequency is 2.5, which is modulating signal frequency. Okay, so determine the bandwidth. So we need to look into the table for beta f equal to 2. Okay, beta f equal to 2. You see that beta f equal to 2, we're gonna have up to 4. Okay, up to 4 pairs of sideband. Okay, up to 4 pairs of sideband. So that means n equal to 4. Okay, so I go back to the slide. Okay, so that means 2 times 4. Okay, times modulating signal frequency 2.5 kilohertz. Okay, so we're gonna get the answer is 20 kilohertz. Okay, 20 kilohertz. So normally we write this bandwidth like this, bandwidth Bessel. Normally we write like this, because you're gonna have another type of bandwidth, which is bandwidth by Carson. Okay, so bandwidth by Bessel is more accurate because it is based on the Bessel function. Okay, you're gonna get another way to calculate the bandwidth is using the Carson's rule, which is so bandwidth by Carson. Carson is a person's name. So he's a mathematician which calculate the approximate bandwidth. Okay, So the approximate bandwidth is equal to 2 delta f plus 2 fm. Or you can write like this, bandwidth Carson is equal to 2 times delta f plus fm. Okay, plus fm. So from here, you actually no need to find the you don't need to refer to the table. Okay, if you want to calculate bandwidth by Carson, you don't need to refer to the Bessel function. Okay, you can straight away calculate using your calculator. Okay, and you're gonna find later that the bandwidth by Carson is less than the bandwidth by Bessel. Okay, you're gonna see later that bandwidth by Carson is actually less than bandwidth by Bessel. Okay, so let's look in the example. Okay, so assuming a maximum frequency deviation of 5 kilohertz, so you are given delta f 5k and maximum modulating frequency, which is fm. The bandwidth would be 2 times. So bandwidth by Carson, okay, bandwidth by Carson is equal to 2 times delta f plus fm. Okay, so that's why 2 times fm plus delta f, so you're gonna get 2 times 7.5k, so you get 15 kilohertz. Okay, 15 kilohertz. So if we compare with the previous example, you see that the value is less. So you see that from this example actually we can calculate the beta. Beta f is equal to k delta f over fm, which is 5k divided with 2.5k. So it is equal to 2. Okay, so this is similar with the previous example. Okay, for beta equal to 2, we get bandwidth equal to 20. But now, for the same amount of beta, when we use Carson's rule, it becomes 15 kilohertz. Okay, so the bandwidth by Carson is less actually. So this example is actually similar with the previous example, but using the Carson we're gonna get lower bandwidth. Okay, because Carson is known as the approximate bandwidth. Okay, so normally in the exam we're gonna ask students to find 2 types of bandwidth. Find the bandwidth by Carson and find the bandwidth by Bessel. So you need to know how to use how to find the bandwidth for both of the methods. Okay. Example 3.4. Okay. Before we proceed, can I get your response? Are you still there? Can you hear my voice? Can you see my screen?
Yes, doctor.
Okay, thank you for the response.
Yes, doctor.
Okay. Because I'm afraid that I'm talking to myself. Okay. So you are still there. That's good. Okay. Okay, example 3.4. For an FM modulator with a modulation index beta f equal to 1. A modulating signal given as VMT equal to VM sine 2 pi 1000 t. So the frequency is 1 kilo. And you are given the unmodulated carrier, which is VCT equal to 10 2 pi 500 kilo t. Okay, So what can we get from this example? From the question, what can we get actually? Okay, so in the question, you are given modulation index equal to 1. You are given Vm, we don't know how much is a peak amplitude of Vm, but we know the frequency of the modulating signal, which is Fm equal to 1 kilohertz. Okay, and we know how much is peak amplitude of carrier, 10 volt, and we know the carrier frequency, which is Fc equal to 500 kilohertz. Okay, so we know a lot of information now. So now we can determine what is the question. The first question say that the number of sets of significant sideband. Okay, how many number of significant sideband? What is the value of n? Okay, what is the value of n? So the number of set of significant sideband, which is n, can be determined based on the Bessel table. This n parameter is determined based on the value of beta. So if beta is equal to 1, so let's look the table. Let's look inside the table. If beta equal to 1, okay, beta equal to 1, that means we have up to 3 pairs of sideband. So therefore n equal to 3. Okay, so the answer for the first question is n equal to 3. Okay, and then what? So for n, for beta equal to 1, okay, from the table, for we can get J0 is equal to 0.77, J1 is equal to 0.44, J2 is equal to 0.11, J3 is equal to 0.02. Okay, this is from the table. Okay, from the table. If you see from the table, this is like this. Okay, the relative amplitude. Okay, the relative amplitude. So why do I write these values? So that it's easy for us to calculate the amplitudes. Remember, this question is about amplitude. Okay, this question is about amplitude. So how can we write the amplitude? How much is the amplitude actually? Okay, so the amplitude, remember, Jn is equal to Vn over Vc. Okay, so now we want to find amplitude. Amplitude is Vn, so Vn equal to Jn times Vc. Okay, Jn times Vc. And since the next question wants you to draw the spectrum, that means we need to know what is the frequency. Okay, so let's do a table so that you can get a clear picture. Let's do a table. Okay, so if I draw a table like this, if I draw a table for each of the j, so for each of the j's, so this is Jn, sorry, so I want to draw a table so that you know what is the value of the amplitude and what is the frequency. Okay, so here we're gonna get how much is the voltage. voltage, amplitude, I put it, wait. So I put here amplitude. Okay, so amplitude, and then frequency, lower sideband and upper sideband. So lower sideband and the upper sideband. Okay, so amplitude in terms of volt, LSB in terms of hertz, USB is in terms of hertz. Okay, so we want to get the clear picture about this. Okay, for carrier, the amplitude is V0 is equal to 0.77 multiplied with Vc, which is equal to 10, given in the question. So this is 7.7 volt. So 7.7 volt is located at where? It's located at the carrier frequency, which is so it is actually located at 500K. So it is not lower sideband, it is not upper sideband, it is the center, which is 500K. Okay, and if we go for the first sideband, okay, so V1 is equal to, so we calculate V0, V1, V2 and V3. This is the actual amplitude. Okay, the actual amplitude. So this is 0.44 multiplied with 10, so we get 4.4 volt. Okay, 4.4 volt. So if you don't want to write the unit, is also okay, because we already write the above title, the caption here, sorry, the header here is a volt, in term of volt. So we understand that this is in term of volt. What about the frequency? Okay, the frequency for the lower sideband is equal to Fc minus Fm. So this is 500K minus 1K. So we get 499 kilo. Okay, 499 kilohertz. Okay, or you can write here in term of so we can write here in term of kilo. Wait, okay, so lower sideband, and we can calculate the upper sideband is equal to Fc plus Fm, which is 500K plus 1K, so it is equal to sorry, this is just put K, never mind, kilohertz, sorry, so just put K is better if we put K over here. Okay, so I rewrite again, sorry. So this is 501 K. Sorry, tak kemas. Wait. This is not a good way to write like this. Wait. I try to write it better. Wait. So that. So this is kilohertz. This is kilohertz for the header. Okay. So 500 for the lower sideband. 500 minus 1. So it is 499 kilohertz. Okay, for the upper sideband, 500 plus 1, so it becomes 501 kilohertz. Okay, and then what? For the second sideband, okay, so V2 is equal to 0.11 multiplied with Vc, which is 10. Okay, so this is become 1.1 volt, and the lower sideband is Fc minus 2Fm. because this is the second sideband, minus 2 FM. So this is 500 minus 2, so becomes 498 kilohertz. Okay, and then here is FC plus 2 FM. Okay, so becomes 500 plus 2, so this is 502 kilohertz. Okay, and then the third sideband is equal to V3 equal to 0.02 multiplied with 10, so this is 0.2 volt. Okay, and the frequency is FC minus 2 FM, which is equal to, FC minus 3 FM, because this is the third sideband. So 500 minus 3 kilo, 500k minus 3k, so you get 498 kilo, 497, 497. Okay, and the upper sideband is FC plus 3 FM, which is 500k plus 3k, so 503 kilohertz. Okay, then what? Draw the frequency spectrum showing their relative amplitude. Okay, so this question, okay, this question supposed to draw the amplitude, not the relative amplitude. Okay, because if you want to draw the relative amplitude, you just need to put the 0.77, 0.44, 0.11 and 0.02. Okay, so I will explain both of it, okay, so that you are not confused. Okay, so when you want to draw, again, as I told you before, don't use ruler. Okay, don't use ruler. It is F versus okay, now we need to know the question. The question said that draw the relative amplitude. That means this is in terms of Jn. Okay, so don't worry, so I just draw here. So this is 0, this is how much? 500 frequency in kilohertz. Okay, in kilohertz. So we have the first sideband, the second sideband, and also the third sideband. Okay, okay. So if the question say like this, relative amplitude, so we can put the values here. Okay, so this is 500, 501, 502, 503. This is 499, 498, 497. Okay, and if this is a relative amplitude, that means we can plot, we can label it as 0.77, 0.44, 0.44, 0.11, 0.02. Okay, so this is if the question say that relative amplitude. What if, okay, what if the question say that you need to plot against the amplitude? Okay, if there's no relative here, that means plot against the draw the frequency spectrum showing the amplitude. Okay, so what happened? That means you need to draw Vn versus F. So if it is a Vn, that means you need to label based on the value of amplitude, not the relative amplitude. So that means this is 7.7. Okay, this one becomes 7.7. Okay, and then 4.4, this is 4.4, 1.1, this is 1.1, this is 0.2, this is 0.2. So this is if the question asks draw the amplitude spectrum. Okay, because there's another one, draw the power spectrum. So if it is a power spectrum, that means we need to find the power for each of the component. Okay, so now I already show you draw the relative amplitude based on the Jn parameter, or draw the amplitude spectrum based on the real amplitude Vn. So it depends on the question. Okay, bergantung kepada soalan. There's also another possibility that the question asks to calculate the to draw the power spectrum. So how to write the power spectrum? That means you need to find the P1, P2, and P3. So you have P0, you have P1, you have P2, you have P3. Okay, so P0 again, power equation is V square over 2R. Okay, that means V0 square over 2R. For P1 is V1 square over 2R. P2 is V2 square over 2R. For power P3 is V3 square over 2R. So we need to know the resistance value. Okay, but this is not the question. Maybe you're gonna see it in the next example. Okay. So that's all for example 3.4. Do you have question to ask? Ada soalan nak tanya tak?
No, sir.
Okay. If you have question, you can ask. Otherwise, I will move to the next example. Kalau ada soalan boleh tanya. Dipersilakan. If you want to ask, please ask. Otherwise, I will show you the next example. Example 3.5. This one. Okay. But before that, maybe we can take a 5 minutes break. Okay. So I will start again at 4:12 p.m. Okay. So we're gonna take 5 minutes break. Okay. Toilet break. Okay. So we meet again at 4:12. Okay. Saya akan sambung pada pukul 4:12. I will continue at 4:12 p.m. Okay. So let's take a break for a while. Okay. You can take a break. 5 minutes. Okay. Shall we continue? Students, are you still there?
Yes, doctor.
Okay, thank you for the response. So I will continue again, okay? So I will continue with example 3.5. Okay, so this example also quite similar with the example 3.4. Okay, hampir sama. So for an FM modulator with a peak frequency deviation, so for an FM modulator with a peak frequency deviation delta F is equal to 10 kilohertz. Okay, I change color. So delta F frequency deviation 10 kilohertz. A modulating signal frequency FM is equal to 10k. The carrier peak amplitude is 10 volt and carrier frequency is 500 kilohertz. Determine the first one is actual minimum bandwidth from the Bessel function. Okay, so bandwidth by Bessel is also known as the actual bandwidth. Okay, actual bandwidth. Okay, so how can we calculate the bandwidth by Bessel? Okay, this is bandwidth Bessel. Okay, so bandwidth by Bessel is equal to 2 times n times modulating signal frequency. So how much is n? So we can calculate n based on the modulation index. So first of all, we need to find how much is the modulation index, beta f. So beta f is equal to delta f divided with modulating signal frequency, fm. So this is equal to 10 kilo divided with 10 kilo. Okay, another 10 kilo. So 10 kilohertz. So this is equal to 1. Again, for beta equal to 1, okay, beta equal to 1, if we see from the table, the number of significant sideband is 3. Okay, 3 significant sidebands. So there's gonna be 3 pairs of sideband. Okay, so back to the slide. So that means this is equal to 2 times 3 times FM is 10 kilohertz. Okay, 10 kilohertz. So this is 660 kilohertz. 60 kilohertz. Okay, 60 kilohertz. And then what? Find the approximate minimum bandwidth using Carson's approximate bandwidth, which is bandwidth by Carson. Okay, which is equal to 2 times delta F plus Fm. So this is equal to 2 times 10 kilo plus 10 kilohertz. So 20 times 2, so becomes 40. Okay, 40 kilohertz. Okay, and then what? Question number 3. Plot the output frequency spectrum for the Bessel approximation. So what is this actually? So this is so the question is supposed to be specific, whether this is an amplitude spectrum or relative amplitude spectrum or power spectrum. Okay, so since the question does not specifically mention what it is, so you can draw the relative amplitude spectrum, or you can also draw the amplitude spectrum. Okay, so let's try to do what we have done previously, like this. So let's try to do like this. Okay, So we have the Jn, okay, we have the amplitude, okay, amplitude in terms of volt. We have the lowest, so this is like this. We have the lower sideband in kilohertz. We have the upper sideband in kilohertz. Okay, so from the Bessel table, J0 is equal to 0.77. Okay, and then we have J1 is equal to 0.44. J2 is equal to 0.11. J3 is equal to 0.02. Okay, and how much is VC? VC is 10, so this is okay, 10 kilo, and the carrier frequency is 500 kilo. Okay, and in order to find the amplitude, so J0 is equal to Vn, wait, so we want to find V0, okay, so V0, so V0 is equal to 0.77 multiplied with 10 volt, so you get 7.7. okay, so there's no upper or lower sideband because this is the center's frequency. Okay, and then V1 is equal to 0.44 multiplied with 10, so this is 4.4 volt. Okay, and this is located at Fc minus Fm, which is 500k minus 10k, so we get here is 490 kilohertz. Okay, 490 kilohertz, and over here is Fc plus Fm, which is 500 plus 10, so this is 510 kilohertz. And then V2 is equal to 0.11 multiplied with 10, so this is equal to 1.1 volt. Okay, and then the location is located at Fc minus 2Fm for the lower sideband, which is 500 minus 20, so we get 480 kilohertz, while for the upper sideband Fc plus 2Fm, so this is equal to 500 plus 500 plus 20 kilohertz, so we get 520 kilohertz. Okay, and then V3 is equal to 0.02 times 10 becomes 0.2. Okay, this is located at Fc minus 3Fm, which is equal to 500 minus 30, so we get 470, and then here is Fc plus 3Fm, so this is equal to 500 plus 30, so we get here 530. Okay, 530, this is 530. Okay, so now we can draw the spectrum. Okay, we can draw the spectrum. So when we want to draw the spectrum again, since this question does not specifically mention whether this is amplitude spectrum, relative amplitude spectrum, or power spectrum. Okay, so you can do any of it. Okay, no problem. Okay, I will show you both of it. So Again, when you want to draw, make sure you draw correctly. Don't use ruler. Okay, jangan guna ruler. So this is F kilohertz. F kilohertz. Okay, so you have here is the carrier. Okay, you have here is the carrier. Okay, and you have the first sideband, second sideband, and the third sideband. First sideband, second sideband, and also the third sideband. Okay, so for example, I want to draw a JN, for example. So I just put the value. So first right here 500, 510, 520, 530. So this is 490, 480, and 470. Okay, so if this is a JN, that means this is 7.7, 0.77, 0.44, 0.44, 0.11, 0.11, this is 0.02, this is 0.02. Okay, so if this is a relative amplitude spectrum. So if you want to draw the amplitude spectrum, just change the value to amplitude. Okay, that means if this is a VN, amplitude spectrum, that means this is 7.7. Okay, as we have calculated in the table. Okay, the value that we have calculated in the table, 4.4, this is 1.1, this is 1.1, this is 0.2, okay, 0.2, 0.2. Okay, so this is amplitude spectrum. And remember, when you want to draw, we want to see first you draw correctly. You have a carrier component and 3 pairs of sideband, correct? Then you need to label. First label the axis, then label the values, the frequency and also the amplitude. Okay, so any question you want to ask regarding this example? If you have question, please ask question. Okay, kalau ada soalan boleh tanya. Okay, so if there's no question, I will move to the next topic, which is deviation ratio, DR. So DR is defined as the mean. So this is what we call as the worst case modulation index. Okay, so minimum bandwidth is the greatest when maximum frequency deviation is obtained with the maximum modulating signal frequency. Okay, so deviation ratio is actually the worst case modulation index and is equal to the maximum peak frequency deviation, okay, divided by the maximum modulating signal. What is this actually? So this is actually the worst case modulation index produce the largest bandwidth. So mathematically we can rewrite the equation to become delta F max. Okay, delta F max divide with Fm max. Okay, so delta F max divide with Fm max. So you're gonna produce actually beta F maximum. Okay, beta F max. So this is what we call as the worst case modulation index. Okay, example. Okay, determine the deviation ratio and bandwidth for the worst case or widest bandwidth modulation index for an FM broadcast and transmitter. For an FM broadcast band transmitter with a maximum frequency deviation delta F max is given as 75K, and Fm max, okay, Fm max is given as 15K. Okay, so determine, this is a this one is a different question, so you can just cancel out this one. So when you want to find the deviation ratio is equal to delta F max divide with Fm max. Okay, so this is equal to 75 kilohertz divide with 15 kilohertz. Okay, so you're gonna get equal to 5. Okay, equal to 5. Okay, and then what? So just cancel the question below and just cancel it. Okay. Okay. If you have question, please ask. Otherwise, I will move to the next topic, which is a very good topic: power in angle modulated signal. Okay. So this now becomes interesting because we are now calculating the power. Okay. So the power in angle modulated signal is easily computed as, so remember the equation for power is still the same like previously, now and forever is still the same, which is V square over 2R or VRMS square over R. Okay, persamaan power ni masih sama dari dulu, kini dan selama-lamanya. Okay, so you see that from here it is calculated as 1 over 2 Vc square multiplied with summation from n minus infinity to n infinity of Jn square from the Bessel function. Okay, so this part is we are going to get it from the Bessel table. Okay, Bessel functions. Okay, and according to the Bessel identity, okay, summation of Jn square from minus infinity to infinity would be equal to 1. Okay, this is according to the Bessel identity. Okay, Bessel identity say that summation of Jn square from minus infinity to infinity is equal to 1. So that's why the power gonna be Vc square over 2. So this gonna, actually there's another one R over here. Sebenarnya ada R. There's R over here actually. But R in this part is assumed to be equal to 1. So that's why they're not putting the R. So actually Vc square over 2R, which is actually equal to the carrier power. Okay, so that means for the angle modulated signal, either it is a frequency modulation or phase modulation, the total power, okay, total power would be equal to the carrier power. Okay, it will be equal to the carrier power. Okay, so thus the power contained in the FM signal is independent of the message signal. This is an important difference between FM and AM. Okay, so we're gonna see about this later. Okay, about in the example. Okay, this one. Okay, so again we can rewrite the equation. The total power, the PC, as we know that PC is equal to Vc square plus, so Vc square over 2R. Okay, Vc square over 2R. Okay, Vc square over 2R is equal to the carrier power. And when we want to calculate the total power, we sum all the components. Remember, when we want to calculate the total power as we have calculated during the AM amplitude modulation, remember that we calculate each of the component. Okay, So if you have a frequency spectrum like this, you need to sum up all the power components. Okay, you need to sum up all the power components. Okay, so that's why here is a carrier component plus the sideband's power. Okay, that's why times 2, because we have upper and lower, so that's why we times 2. Okay, kita darab 2 kerana ada 2 bahagian. Okay, so P total here again, P0 is the carrier component, which is equal to V0 square over 2R. Okay, V0 square over 2R. Okay, this is the carrier component. Okay, and then for the sideband, V1 square over 2R, V2 square over 2R plus V3 square over 2R until Vn square over 2R. And as we have learned previously, what is V? Voltage amplitude is equal to relative amplitude multiplied with carrier voltage. Then we can get the real amplitude. Okay, as I mentioned previously, that Jn is equal to Vn over Vc. Okay, so when we want to calculate the amplitude, we just multiply the relative amplitude with the carrier voltage. Okay, and if you see from here, okay, so since every Vn, every V, V1, V2 so every V, V1, V2, V3 and so on, it has the carrier component, carrier voltage. Okay, so what happened actually? So for example, like this one, so this is a V1. V1 is actually J1 times Vc square. So this is V2 is J2 times Vc and then square. Similar here, V3 times Vc, sorry, J3 times Vc. So wait, so J3 times Vc square until Jn times Vc square. Okay, so you see that even for V0, V0 is J0 times Vc square. Okay, so if you see from here, it has a, for example, here is Vc square over 2R. We have here another one is Vc square over 2R. Another one here is Vc square over 2R. Vc square over 2R, which is the carrier power actually. Okay, okay, so Vc square over 2R is actually equal to carrier power. Okay, so that's why each of these has the carrier power. So J0 square Pc plus 2 times J1 square Pc, J2 square Pc plus J3 square Pc until Jn square Pc. Okay, so you will be surprised later that all of this is actually equal to Pc. Okay, all of this actually equal to Pc. Okay, and if you use the table in your notes, okay, the Bessel table in your notes, you're gonna get values slightly different. Okay, so that's why it use the approximate over here. Why? Okay, so in this slide it shows that when you use this complete equation and you compare with the carrier power, you're gonna get slightly different in terms of a decimal point. For example, if you do the total calculation like this, you're gonna get 5.05 watt, for example. But when you calculate the PC, you're gonna get 5.01, for example. So the difference gonna be 0 point something watt. Very small. Why is it like that? Because theoretically it said that it is equal to PC. Why I didn't get the PC? Kenapa saya tak dapat sama dengan PC? Okay. So there's another there's gonna be example about this. Wait, you see that the statement below here, the total power in the carrier and the sideband components approximately equal to the unmodulated carrier power. But theoretically it is equal. Okay, theoretically it is equal. But why in the notes it say approximately? Okay, kenapa dalam nota ini dikatakan approximately? Why? Because okay, remember theoretically the total power is equal to the PC. Theoretically, okay, because we have seen about this. Okay, but if you use the Bessel table in your notes, you will get approximately equal. Why? Because in the so I flashback. So because in the table, okay, this table has neglect the value less than 0.01. This table has removed all the values less than 0.01. So that's why in your calculation later, even in the example, you're going to see the difference, very small difference. Okay, for example 5.005 and also 5.001, very small. Okay, it's not 5 and 6, not like that, just very small decimal point, the difference. Why? Because this table has neglect the value less than 0.01. Okay, but remember the theory is it's supposed to be equal to the PC. Okay, so the question is, in the exam, what should I write? Okay, what should I write? Okay, so in the exam, you can choose either you want to do complete equation like this, or you want to just to write equal to PC. Both are correct. Kedua-duanya adalah betul. Tidak ada masalah. There's no problem. Okay. In the exam, when you are asked to calculate the total power, you can directly calculate as PC, or you want to do one by one. No problem. Both will give the same answer. Even though it is slightly different in terms of decimal point, so there's no problem about that. Okay, so tidak ada masalah untuk menggunakan jalan panjang atau jalan pendek. No problem. Okay. So we have another few minutes. I will continue. Example 3.7. So let's do 3.7. Okay. So we're gonna use all the time that we have to study. Okay. So no problem, because next week is a public holiday, right? Wesak Day. Okay, next week you don't have class, so next week is a Wesak Day, public holiday. Again, I will give you the recording maybe. Okay, and for your information, section 1 is supposed to be taught by Mr. Ezri. Okay, but he's on long holiday previously, and he already continued this week. So I assume that after the Wesak Day, he will take over this class from me. Okay, so the next class would be by Mr. Ezri. Ezri akan Encik Ezri akan mengajar topik seterusnya. Okay, so example 3.7, an FM signal is given as VFMT equal to 12 cos okay, 12 cos 6 pi times 10 power of 6 plus 5 sine 2 pi 1250t. Okay, so you see that you are given the complete equation. From here, actually you can determine what are the parameters. Okay, so you are given the VC. Okay, this is VC. Okay, and you are given this one, because this is 2 pi f. This is supposed to be 2 pi f. Okay, 2 pi fm. That means you need to divide with 2 pi. So you get the, if you divide with 2 pi, you're gonna get 3. So fm, so fc here is 3 mega. Okay, fc here is the 3 mega. So from here, actually I can I can find the f. Sorry, yeah, this is supposed to be fc. Okay, this is fc. So if I divide with 2 pi, I'm gonna get fc equal to 3 megahertz. 3 times 10 power of 6. So 3 mega plus 5. What is this? Okay, this is actually referring to the beta f. Okay, what is this? This is modulating signal frequency, FM. Okay, so we can determine the rest of the parameters. Okay, A, find the frequency of the carrier signal. So we already get the frequency of the carrier signal, which is 6 pi times 10 power of 6 divided with 2 pi. So we get 3 megahertz. Okay, modulating frequency of the modulating signal. So this is straight away from the question. So we get 1250 hertz. Okay, 1250 hertz. Modulation index, also straight away from the question, equal to 5. Okay, beta f equal to 5. Frequency deviation. How to calculate the frequency deviation? Delta f is equal to, so remember that beta f is equal to delta f divide with fm. So if you want to find delta f, this is equal to beta f times fm. Okay, beta f multiplied with fm. Okay, so delta f, so this is delta f is equal to beta f 5 multiplied with fm is 1250. Okay, so we get this one, how much? So 5 times 1250, 6 to 6 to, okay, so this is frequency deviation, yeah. So beta f is equal to delta f is equal to beta f multiplied with fm. So delta f is equal to 5 times 1250, so you get here is 6250 hertz. Okay, delta f. Okay, and then what? Find the power dissipated in 10 ohms resistor. So this is about the total power. You need to find the total power. So remember, total power is equal to, so we can write equal to Vc square over 2R, which is equal to Pc. So this is equal to Vc is 12 square divide with 2 times 10. Okay, .2 watt. Okay, 7.2 Finish. Okay. So if you have question, you can ask. Otherwise, I will move to the next example. Okay, next example 3.8. Okay, kalau ada soalan boleh tanya. If you don't ask, I assume that you understand this, and I will move to the next example, the last example before we can stop. Determine the unmodulated carrier power. Okay, that means you need to find PC for an FM modulator given that beta is equal to 1, VC10, R10, R equal to 50 ohm, then determine the total power in angle modulated wave. Okay. Okay, so for beta equal to 1, okay, for beta equal to 1, we're gonna get for beta equal to 1, based on the Bessel function n is equal to 3. Okay, so okay, so this example actually wants to show you the difference using the long equation compared to the power equal to PC. Okay, example ini sebenarnya nak tunjukkan perbezaan itu, perbezaan antara jawapan yang diperoleh dalam menggunakan persamaan panjang compared to the power calculation using the PC. Okay, so we're gonna calculate one by one, because this example wants to show you the difference. Okay, so J0 is 0.77, J1 is equal to 0.44, J2 is equal to 0.11, J3 is equal to 0.02. Okay, and from here we can actually calculate V0 is equal to, oh sorry, we can calculate like this, wait. Okay, so P total is equal to J0 square PC plus 2 times J1 square PC plus J2 square PC plus J3 square PC. So we need to find the PC. So PC is equal to VC square over 2R. So PC is equal to VC square over 2R. So this is 10 square divided with 2 times 50. Okay, so this is equal to 100 and also 100. So this is 1 watt. Okay, so here is equal to 0.77 square. This is 1 actually, okay, plus 2 times in bracket 0.44 square times 1 plus 0.11 square times 1 plus 0.02 square times 1. Okay, close big bracket. So how much is this? So let's try to use your calculator. 0.77 square, 0.77 square, 0.595929 plus 2 times. So how much is this? 0.44 square plus 0.11 square plus 0.02 square. So you're gonna get this one 0.2061. So please correct me if I'm wrong. Okay, tolong betulkan saya kalau saya salah. Okay, so you need to 0.2061 multiplied with 2 plus 0.5929. So you're gonna get 1.0051. Okay, so compared to PC, remember PC is equal to 1 watt. Uh, so that's why the statement below here, it is not exactly equal to PC, not equal to PC, because the values in Bessel table has been rounded off for value less than 0.01. Okay, the Bessel table in your notes has rounded up, has removed the sideband values less than 0.01 because it is very, very small, so it has been neglected. Okay, so this example just want to show the difference. Okay, so you see that the difference is very small. Okay, the difference is very small. Okay, so that's why I told you in the exam you can choose either one, no problem. You can write using the long equation, or you want to write using the carrier power, no problem. Okay, so this example just want to show the difference. Okay, because why there's a difference? Because we have rounded up the values in the Bessel table in your notes. Okay, if you see in the internet, so if you have time, if you have free time, browse the internet, looks for the Bessel table. You're gonna get the complete table of Bessel, which is more accurate. Okay, lebih accurate. Okay, so example 3.9 is very long. Okay, so this is a good example for the final exam actually. 3.9. Yeah, we will do this later. 3.9. Okay, not now, because it's already 3 minutes to 5 p.m. So I just want to share, because this is a good example for the final exam. If you see that the pattern is something like this in the final exam, where we ask you step by step, calculate this and then calculate this, and so on. And normally at the end we're gonna ask you to find the power. Okay, because power normally we ask at the end normally. And we also ask to draw the spectrum and then the rest of the parameters. Okay, so the question is something like this. Normally we ask in the final exam. So if there's normally we give you a figure, a picture, so that you need to analyze the equations. You need to analyze the equations. From the equation, you need to calculate all of these parameters, something like that. It's not a straightforward like this. Normally, we give you a block diagram. Okay, you need to determine the equation first. Determine the equation first, the complete equation. Then from there, you can calculate step by step all the parameters. Okay. If you remember about single sideband example that we have calculated previously, that we have done previously, about single sideband, where we find the equation at point A, point B, point C, point D, something like that, and then we can calculate the rest of the parameters. Okay, so you can see from the, you can read, you can learn from the previous questions. Okay, so it's already 5 o'clock, so let's take the attendance. Okay, so you can open your QR code. Open your QR code, you can scan the attendance, and then you can go to anywhere you like. Okay, remember that we have tests on Friday, so hopefully you still remember that you have tests on Friday. I repeat again, you have tests on Friday, so make sure you study properly for the test. Okay, I hope that you can score the test. Okay, my intention is to give you A for this subject, so you need to have effort to study. Okay, Later I will give you the exact topics that you need to learn so that you can more focus on that specific topic. Okay, so that's all for today. Thank you. See you again next time. Okay.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doktor.
Welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Thank you, Doktor. Selamat Hari Raya, Doktor. Thank
Selamat
you.
Raya. Welcome.
Thank you, Doctor.
Welcome.
Doktor,
Hiya.
saya tak dapat scan QR code tu.
Nama siapa?
Amirul Haziq.
Amirul Muhammad. Amirul Haziq.
Muhammad Amirul Haziq.
Okay, Amirul Haziq. Okay, done.
Doktor,
Okey,
saya juga
terima kasih,
Doktor.
Doktor.
Muhammad
Ah,
Ahmad
Doktor,
Wakil.
saya pun tak boleh scan.
Okay, one by one. Siapa nama?
Muhammad
Muhammad
Firdaus
Akmal.
bawah tu.
Muhammad Firdaus.
Okey,
Okay,
Firdaus,
done.
Firdaus.
Okay,
Okey,
next.
Doktor.
Muhammad Akmal Hakim, Doktor.
Akmal.
Nombor
Okay.
14.
Okay, done.
Thank you, Doktor. Selamat Hari Raya.
Okay, selamat raya. Any more? Siapa lagi?
Doktor,
Ya.
nak tanya,
Okey.
minggu ni Jumaat saya ada test subjek lain. So
Subjek.
dia pukul 8.
Aha.
8 sampai 10.
Okay.
Lepas tu isi yang subjek ni pukul 10. Dua subjek.
Subjek apa?
Boleh ke doktor macam tu?
8 sampai 10 subjek apa?
Computer architecture subjek lain.
Oh, kenapa you tak bagi tahu saya sebelum ni?
Tak ada, lecturer tu kata 8 hingga 9.30 je.
Oh, 8 sampai 9.30. Oh, okay. So nanti saya tukar masa dia lah. Mungkin either selepas you punya test atau maybe waktu petang ke? Is it okay?
Boleh doktor.
Okay. Macam mana you punya computer architecture tiba-tiba boleh buat hari ni, hari Jumaat?
Tak, hari tu lecturer tukar masa, so saya baru perasan dia apa?
Yalah. Sebab saya dah upkan lama, saya yalah tarikh 13 hari bulan tu dah lama dalam auto sebenarnya. Tapi tak apalah, saya cuba tukar. So you pukul 10 tu you sepuluh dah habis lah, betul lah
Dah habis lah. Lepas tu start yang subjek ni lah.
Okay, so let's see whether maybe we can do in the afternoon maybe. Okay, so that tak ganggu you punya masa test lah. So berdiri
Okay,
you punya test
doktor,
Ya.
tak dengar doktor?
You punya test ada banyak lah.
Doctor, can you help me with the attendance?
Yeah. What's your name?
Ahmed Samir.
Ahmad Samir. Okay, Samir, done. Tadi siapa yang tanya test tadi?
Saya doktor.
Ya. So you punya test ada banyak Khamis ada test, Jumaat ada test.
Kami satu subjek aja. Jumaat subjek ni dengan subjek lain satu. Dua subjek.
So macam mana tu? Semua nak buat ni So okay, tak apa, saya cuba buat petang atau malam ke? Is it okay?
Okay doktor.
Itulah saya sebenarnya not prefer a weekend because it will disturb the students' time, but there are a lot of tests will be conducted on Thursday. Thursday is the most suitable time actually. So okay, saya cuba anjakkan bagi you masa sikit lah untuk rest sekejap ke lepas tu, and then you boleh ambil test lah. Boleh
Okay doktor. Thank you doktor.
Okay, all the best to you. Okay. So any more 2 students absent Okay, 3, 2, 1. Okay. So that's all for today. So Syahmi dengan Ikmal dalam attendance belum Syahmi Ikmal. Syahmi and Ikmal. Ikmal dengan Syahmi Nordin. Ikmal datang, Syahmi. Syahmi dah, Ikmal dah. Okey, seorang tak datang lah, seorang tak datang. Siapa ni? Aizat Syafiq Sanusi. Okay, so that's all lah. So I stop sharing and then we can close this one and for call for everyone. Okay, stop.